Okay, so I'm going to go all the way through from start to finish of an example of pressure-driven flow through a narrow rectangular channel to try to figure out the velocity gradient, the velocity profile, and the shear stress profile, and the flow rates and average velocity and things like that. So we discussed this problem in class and came up with some assumptions. I have them listed here. I'm not going to go back over them. And we obtained a momentum balance and governing equation from a momentum balance. I also give an example of this in the momentum balance video, as well as for pressure-driven flow. So I'm not going to go over these two, but here they are if you want to look at them. What I am going to go over is the rest of the problem, though. So back to, this is our governing equation. The pressure gradient in the x direction equals the shear stress gradient in the y direction. Since these two are equal, what I'm going to say is that the pressure gradient dP dx is equal to C1, some constant. So if we integrate dP, integrate P over x, we got P equals C1 x plus C2. Our two integration constants. We're going to define our boundary conditions in this case as the entrance to the channel is going to be x naught and our exit is going to be xl, and therefore our pressure at the entrance is P naught and our pressure at the exit length L is PL. So we should be able to, we can define the change in pressure as P naught minus PL, and the total length of our system is XL minus X naught. So we want to be able to prove this equation right here, and how we're going to do it is just use our boundary conditions and solve for C1 and C2 so that we know what our pressure is. So the first boundary condition, P naught is equal to C1 times X naught plus C2. So therefore C2 is equal to P naught minus C1 X naught. If we plug that back in the equation and use PL, so we have PL C1 X times XL plus C2. Therefore, with both of those equations, we can narrow down just C1 is our only term of unknown, and we can then see that it is, we move the P naught over here, PL minus P naught equals a C1 XL minus X naught. So again, PL minus P naught is defined as change in P, and XL minus X naught is L. Therefore, we get C1 equals negative delta P divided by L. So again, the pressure gradient in the x direction is equal to a constant. That's what we said before, and we found that that is going to be equal to delta P divided by L. Alright, so now we have this equation as our governing equation. We just derived this left-hand side to be this, a constant term. We want to go ahead and determine the shear stress and the velocity in the channel at any given location in the channel. So how are we going to do that? We're going to integrate tau in terms of y. So the integration looks like this, with C3 being our, I'm just going in order from the other constants I've used before. So we integrate, and we're going to use our boundary conditions that we know of to be able to solve this equation. So we know the no slip condition at y equals h divided by 2 at this point right here. The no slip condition holds, so Vx equals 0, as well at this other boundary point y is equal to negative h over 2, the Vx is equal to 0. So here's two simple conditions at both of our boundary points that we can use. And our constitutive relationship that's going to help us solve the equation is that the shear stress is equal to the viscosity times the velocity gradient. So this is for Newtonian fluids. So using the constitutive relationship, the equation, and the boundary conditions, we can prove this is our velocity profile. So here's our constitutive relationship, our equation we just solved, and we relate those two to one another. So we have this relationship. We can now solve for Vx by integrating. So here's the integral for Vx. Just integrate in terms of y. So now we have another constant of integration. And now we're going to plug in one of our boundary conditions at y equals h over 2, Vx is equal to 0. So we plug those in, and we are able to figure out C4 in terms of C3. Just a little bit of algebra. Now we plug in C4, we have Vx in terms of C3s. So now we can plug in our other boundary condition, y equals negative h over 2. At that point, Vx is equal to 0. So we plug in 0 here and negative h over 2 into there, and we find out that this is our equation. So we have only one unknown, and that's C3. So now we can solve for our integration constant C3. So you can kind of get the picture that when you do the algebra, move it around, it's really easy to see that C3 is going to end up being equal to 0. So now go back and we have this equation right here where we have Vx in terms of only C3. So this is going to go to 0 and this is going to go to 0. So then Vx is just going to be equal to these two terms here. And you do the algebra, and this is our velocity profile for the pressure-driven flow through a rectangular channel.